This is the first video explaining in detail the approach of creating artificial digital life. If you haven't seen the trailer for this series, I would recommend to do so. The trailer outlines the goal and scope of this undertaking. A general guideline for my approach is to keep it clean and simple. Complex structures should emerge by themselves, not because complexity was built into it right from the start. Let's have a look at the world and the organisms. The world consists of discrete positions, represented by screen pixels. Empty positions are black. Positions containing a package of food are white. Cells also cover exactly one position and are of green color. For better visibility, a larger screen circle is surrounding them. This circle is just for visibility, it's not part of the actual world. The world itself is circular. The next position left of the left edge is the rightmost position. The same for up and down. This way, organisms can spread all over the world without running into borders. In the beginning, cells are very simple. They are born onto a certain position with a little amount of energy. If that position holds some more food, their energy level can reach a point at which they can reproduce. The offspring will always be placed at a position next to the cell. So cells can spread, but individually they do not move at this point in time. What might appear as a movement is spreading, just like a forest spreads without individual trees moving. As cells lose a little energy over time, eventually they might end up dying and disappearing if no new food is supplied. That's what we have seen in this animation. The world ran out of food and all cells went extinct. On the other hand, if food is too scarce right from the start, no population will build up at all. The few initial cells we position in the world will die out immediately. For a population to be stable over time, we apparently need recurrent feeding. But again, it depends on the amount of food. Despite recurrent feeding, the initial population simply dies out in this simulation. Increasing the food supply by roughly 10%, we see life persist a little longer, but also in this case, eventually all cells vanish. Only after 5% more again, we reach a population which is stable over time. Well, as you can tell from the graph, it's not all that stable. After some time, the system is getting rather fragile, with a population exploding and then almost vanishing again. Of course, we could simply provide more and more food, but the result would not be very interesting. The world would just be flooded with cells. One way to address this is to provide food only to specific regions. Imagine food going through a filter. Only through the black parts, food will fall into the world. Now cells populate the inner circle. But despite the fact that there is plenty of food in the outer circle as well, cells are not able to reach it at this stage. Another way to address the issue is by changing the distribution. Up to now, food was provided evenly distributed over the world. As an alternative, we can use a normal or so-called Gaussian distribution instead. More food will accumulate in the center and less food in the outer regions. Now cells may grow and spread, but there's a natural limit to their spreading. It leads to a dynamic and still very stable population. As we can see from the graph, the population is trending around 300,000 cells. Such a stable population should be the perfect base for further developments, especially the development of a genome steering movement. With the ability of movement, cells should become able to conquer regions of the world currently abandoned. This will be the topic of the next video: the development of a genome which enables and optimizes the movement of these organisms. So stay tuned and don't forget to subscribe.